Hi, I'm Ryan Baker, and this is Big Day in Education. Today, we're going to talk about advanced classifiers. So classification, let's review it really quickly. There's something you want to predict, the label, and the thing you want to predict is categorical, or binary. The answer is one of a set of categories, not a number. So we talked about a lot of previous methods so far this week. K-nearest neighbor, K-star, decision trees, decision rules, step regression, logistic regression. These are all conservative algorithms that don't attempt to capture all the variance in the data. And frankly, most of the work in educational data mining has used these kind of algorithms because they tend to work pretty well for educational problems. Most of what we've talked about has been in reference to these algorithms because these algorithms usually do better in most educational data mining than less conservative algorithms due to the properties of educational data. In brief, educational data has lots of systematic noise. But that said, there are clear places for some of the less conservative algorithms, more modern ones if you want to say it like that. One of those algorithms is support vector machines. Support vector machines conduct dimensionality reduction on the data space, which is to say that they take a large number of variables and collapse it down to a smaller number of variables, and then they fit a hyperplane which splits the classes. So if you think about 2 dimensions, you might have a plane, a line cutting across the split. When you have 3 dimensions, you'd have a plane cutting across the 3 dimensions. When you have 17 dimensions, you have a 17-dimensional hyperplane. So for example, a 346-dimension cloud of data might become a 7-dimension cloud of data. And then the data is split into 2 groups by a hyperplane cutting across the 7 dimensions. This creates very sophisticated models. It's great for text mining because in a linguistic corpus, there might be literally thousands, tens of thousands, hundreds of thousands of words that might occur. We need to collapse that down to a smaller number of dimensions. It's great for sensor data where there's a lot of different inputs coming in. It's not commonly used with most other types of educational data at the moment. It's not, for example, used with logs or grades or interactions with software very often. Another less conservative algorithm is random forest. In random forest, we split the training data into random subsets of the data points. And then for each subset, we take a random set of the data features. We build the decision tree, doesn't really matter which algorithm, on the resultant data set, and we take all the trees together then, and each tree gets 1 vote, we go with the majority vote. Random forest is often used for ensemble models where you want to take a number of models and put them together so that actually you're having a collection of votes on a collection of votes. Neural networks compose extremely complex relationships through combining what are called perceptrons. They find very complicated models. Here's an example from Soller and Stevens, where they show a neural network showing the 36 nodes, each one describing a different subset of their data population. One popular variant on neural networks is recurrent neural networks, also referred to as deep learning. In deep learning, you try to fit sequences of data rather than single data points, using a neural network to do so. It can be thought of as a type of neural network where you have partial propagation of information over time. So you kind of have a neural network that is not just rebooting itself at every data point, but actually takes part of the information from the last time, using a very complex fit function to do so. Recurrent neural networks are commonly used to represent language over time, with sentences and paragraphs represented as sequences of words. They're also used in the somewhat controversial deep knowledge tracing, which we'll discuss in week 4, where they measure the change of knowledge over time. Recurrent neural networks have also been used in new detectors of student emotion, which are thought in initial analyses to be significantly more accurate than previous models. This is a good case to use deep learning because there are reliable trends and patterns in emotion over time which can be captured, and quite frankly, even with conservative algorithms, most affect detectors are completely incomprehensible to interpret because the patterns that they're leveraging are kind of second-order effects on the student behavior. So with that, we've completed our discussion of week 1. Thank you very much for making it through the first week. In week 2, we'll be talking about issues such as how do we know if a prediction model is any good? We'll talk about goodness metrics, model validation. So thank you very much for coming. I'm Ryan Baker. This is Big Day in Education, and I'll see you next week.